Hello everyone, welcome to section 2.2. This will also be a supplement I'll attach in this week that has some good problems from this section. But we're going to be talking about these things called piecewise functions. Now, piecewise functions appear all the time in calculus, and understanding how they work, it's not too difficult, but understanding them and getting some good practice with them will really help you out when you get to calculus. Okay, so let's see what a piecewise function is. What I like about piecewise functions is what they are. It's really a recipe of combining functions and different pieces of graph and slapping them all onto one graph. So I guess the definition of a piecewise function is a function that's defined by more than one function on a specific interval. Let me show you the notation of a piecewise function, and then we'll go ahead and work with them. Let me erase a little bit what we have here. Okay, so a lot of what we're going to be doing with piecewise functions, graphing them and evaluating them, and also talking about their domain and range. So our first example of a piecewise function, so I guess our first example of what they look like. So I'll write f of x, okay. Now when we write a piecewise function, I'm going to go ahead and make a list here. So let's go ahead and make a list. Okay, so I use this one curly bracket. It's not very common. Actually, I've never seen it where a piecewise function is defined and they close the parentheses. You always start out with one kind of a, curly bracket, and then you make a list of the functions in here. So this piecewise function, what does it look like? The graph looks a lot like the graph x plus 2, but now I need to say it's the graph x plus 2, but what's the interval? It looks like x plus 2 in the interval. Sometimes you'll see a comma here, sometimes you'll say if. So if or a comma means the same thing. F of x looks like x plus 2 if x is strictly less than negative 2. So on the interval for x at negative 2, well, not exactly at negative 2 because it's less than, but if I'm looking to the left of negative 2, the picture of the graph looks just like x plus 2. Similarly, let's say this graph looks like x squared plus 2, okay, let's say if x is greater than or equal to negative 1. So this is what a piecewise function looks like. There could be 2 pieces in here, there could be 3 pieces, there could be 10 pieces. But what has to be true is that these intervals over here cannot overlap. Okay, so let's just go ahead and first draw a sketch of this and we'll talk more about it. Okay, let's give a sketch of this. So how do I like to sketch piecewise functions? What I'm first going to do is let's graph the function x plus 2. So this is a line, it has a slope of, this is a line, has a y-intercept at 2. So it has a y-intercept at 2, it has a slope of 1. So if I go over 1, I would go up 1. So the graph has the coordinate 0, 2, 1, and 3. Or if you'd like, notice if I plugged in negative 2, I would get an output of 0. So here's negative 2. Okay, so if I wanted to graph this, graph the entire thing, this purple line right here is the graph x plus 2. But I don't want the entire graph. I only want a portion of it. I only want a portion of the graph that is less than x equals negative 2. So I only want this portion of the graph. Anything bigger than negative 2, I want to erase. So let's go ahead and do that. Let's erase this. I don't want this piece. Okay. So at 2. Okay. Now notice here specifically what it's saying here is it's saying that this function is defined for x strictly less than negative 2, not exactly at the value negative 2. So I won't have a closed-in bubble right here, I'm going to have an open bubble. So I just want the graph just to the left of negative 2, not including negative 2, that's why I have that open bubble there. Okay, let's draw the rest of the graph. So what does the rest of the graph look like? It looks like x squared plus 2 for x bigger than negative 1, bigger than or equal to negative 1. Okay, so if I graph the whole thing, this is a parabola that's been shifted up 2 units. So the graph would look like this. If I plugged in 1, would I get an output of 3? So here's a couple points here. It's going to be a parabola. It's going to be a happy face parabola. It's going to be a happy face parabola. But I don't want the whole graph. And also notice that there's a slight problem if I graph this whole thing. That's why these intervals can't overlap. Is notice here that this is no longer a function because it's not passing the vertical line test. For this input, I'd be getting 2 outputs. So that's why these intervals can't overlap if it's going to be a function. So I really just want the graph of x squared plus 2, but I only want it for x bigger than or equal to negative 1. So at negative 1, if I plugged in negative 1, I get what? Negative 1 squared, I get 1. Plus 2, I get an output of 3, so that's right here. Notice I'm including negative 1, so if I plug in negative 1, the output will be 3. So I'll put a closed dot here. And anything that is to the left of negative 1, I will erase. And here we have it. This is the graph of this piecewise function. So this is the graph of f of x. Notice it's a piecewise function because this function is defined differently on different intervals. Okay, so let's go ahead and talk a little bit about this function. Let's talk about its domain. Okay, that's the domain, so I'll put a D here for domain. Remember that domain is the set of all allowable inputs. There are values I can plug into the function that actually give me an output. So I'll go ahead and write the domain here. How about I do it in set builder notation? Maybe I'll do it in a couple notations if you haven't seen these types of notations before. But if I'm using set builder notation, the domain of this function f, I'll go ahead and write a curly bracket. Domain has to do with the x values, so I'll record an x here and put a bar. So this means the domain is a set of all x values. This bar can be read as such that, so the domain of this function is all values of x such that, now what I'm going to put over here is I'm going to list the conditions on x. Well, what's true here? Well, I can hopefully see here that what must be true is the domain must be all values less than negative 2 and all values bigger than negative 1. So I can look at the graph here. What are my allowable outputs? Well, if I plug in negative 1, I'm going to get an output. And anything to the right of negative 1, I get outputs. Notice here that I don't have any outputs for like negative 1.5. There are no outputs here. So from the interval from negative 2, not including negative 2, the interval from negative 2 all the way to negative 1 is not in my domain. I can't plug in any inputs here to get an output. So the domain is anything bigger than negative 1, including negative 1, and anything less than negative 2, not including negative 2. So that's the domain of this function. This is called set builder notation. Set builder notation. Okay, you could have also used what's called interval notation. When you talk about interval notation, you record the intervals. So this function is defined. Okay, it's defined from negative infinity all the way to negative 2. Okay, so let's talk all the way from negative infinity all up to the way to the negative 2. I put a curly bracket, or I'm sorry, a soft round bracket when I'm not including a number. And then what I do is I put a little u here. Okay, it's this interval, but I'm also including, this means and, I'm also including the values from negative 1 to infinity. Okay, but I need to be a little bit careful here. I shouldn't put a round bracket on negative 1 because negative 1 is in my domain. Plugging in negative 1 gives me an output of 3. So I'm going to put a square bracket here. So that's how you could write the same domain in interval notation. Let's talk about the range. So this is the domain. Okay, that's the range. I'll put R of f. So this is the range of the function f. Now I just want to list all my possible outputs. So what I like to do when I'm running all my possible outputs is I take a horizontal line and I run it through and I figure out, well, what y values does this horizontal line hit the graph? So it looks like from negative infinity, and I guess maybe what I'll write here is the outputs have to do with the outputs, f of x. You could also put a y here. So all f of x, all outputs such that, well, they go from negative infinity all the way up to 0, or you could say anything less than 0 I'll get is an output. So how about all x less than 0? So I'm basically from negative infinity all the way to 0. Okay, I don't get any outputs between 0 and up to 2, but not including 2. So I do get an output of 2 all the way to infinity. So x greater than or equal to 2. So this would be my range. Okay, I could also write this as going from negative infinity all the way up to 2, all the way up to 0, from negative infinity all the way up to 0. And also, I'm going, looks like from 2 all the way to infinity. And it's including 2. So that's a way that we can write the domain and range of this piecewise function. Okay, so let's also evaluate this function. Let's evaluate this. Oh, I guess I made a little bit of a mistake here. When I wrote f of x such that I shouldn't have wrote x values here. I should have wrote f of x because I'm talking about my outputs. There we go. That's correct. Okay, let's go ahead and do some evaluations of piecewise functions. Okay, so let's evaluate this function. Let's say, what is f of 3? So we want to do some evaluations. Now, oftentimes when I evaluate a function, I usually am not going to be looking at the graph. I usually just look at the formula. So I want to plug in the value of 3, but I have to know which version of the function to use. So notice that 3 here, well, 3 is not less than -2, but 3 is bigger than -1. So when I plug in 3, I'm going to use this version of the function. So when I'm evaluating this function at 3, 3 is bigger than -1, so I'll use this version. So I'll write 3 squared plus 2, so that gives me 9 plus 2, so I get out an 11. Okay, let's go ahead and evaluate this function. How about at -4, for example? Okay, we should note that -4 is less than -2, so I want to use this version of the function. So I'll evaluate the function. I'll replace x with -4, so -4 plus 2. -4 plus 2, I get out -2, so that's how we evaluate. Let's do one more. How about we do f? How about f of -2? Let's try to plug in -2 into this function. Okay. Notice that this function is not defined at -2. Notice this function is only defined for x strictly smaller than -2 and x bigger than or equal to -1. -2 is not in the domain of my function. Notice here if I plug in -2, there is no output. So what we say here is this is undefined. This is undefined. Okay, let's do another example. Okay, let's say I have a piecewise function. Let's say it's f of x is equal to, let's say the function is -2. Let's say if, or you can put a comma, you might see either one. If x is less than or equal to -3, the graph looks like 4 minus x. Let's say if x is between -3, not including -3, -3 to 0. And let's say the graph looks like x if x is greater than or equal to 2. Go ahead and pause the video and try to graph this piecewise function on your own. Okay, let's do it. So let's go ahead and draw a sketch. Okay, let's start with the first function. So the graph is -2 if x is less than or equal to -3. So let's mark -3 here. And now whenever I plug in a value into my function that's less than -3, the output is always -2. Okay, I'm including -3. So I will record that when you plug in -3, you actually do get an output of -2. And you're going to get an output of -2 for anything less than -3. So there's the first part of our function. Again, you could have drawn the whole line and erased if you wanted to. Okay, so now what's going on between -3 and 0? So now I want to go between -3 and 0. Okay, well the graph looks like 4 minus x. If you think about the graph 4 minus x, if you would like, you could think about this as plus the opposite. You can switch the order of addition, so -x plus 4. So we can think of this is a line. It has a y-intercept of 4 and a slope of -1. So let's go up to 4. So at 4, if I were to plug in 0, I would get an output of 4. But let's be a little bit careful here, because notice, if I notice that if I do plug in 0, notice that 0, well, this 4 minus x is not defined at 0, but if I were to plug in 0, I would get an output of 4. But I'm just going to go and put a open dot here. Okay, now it has a slope of -1, so if I were to, I guess what you could do, since you know it's a line, if you wanted to, you could plug in the left bound, x equals -3. So if you plug in -3, you're going to get a -3 plus 4. 4 plus 3, you're going to get out 7, so 4, 5, 6, 7. So if you plug in -3, you would get an output of 7. Okay, but notice that the function 4 minus x is not defined at -3, so I'll put an open dot here. Now since it's a line, these must be connected. Okay. So this is the graph of 4 minus x on the interval from -3 to 0, but I'm not including -3 and I'm not including 0. That's why I have open circles at the endpoints of this line segment. Okay, now let's think about for bigger than 2. 1, 2. So if x is bigger than or equal to 2, it looks like the graph of x. So this is a line, it has a y-intercept of 0 and a slope of 1. Or you could think about it, whatever input I plug in, the output is the same. So if I plug in 2, my output is 2. If I plugged in 3, my output would be 3. So I can connect these lines. So it's y equals x, or f of x is equal to x for x bigger than or equal to 2. So that's what that line will look like. And there we have it. Here's our piecewise function. Okay. Let's go ahead and find the domain of this, the domain and range. Go ahead and pause the video and find the domain and range of this function. You can write it in either notations if you'd like. Okay, so let's go ahead and talk about the domain. So I'll write the domain of f. I write it right here. The domain of f. Okay, that's going to be all x values such that, well, what can I plug in? I can plug in any value. Where will I get a meaningful output? Well, I'll get an output for plugging anything less than -3 all the way up to -3. I still get an output. But I'm also still getting outputs all the way to 0. So my domain is going from -infinity at least all the way up to 0. Okay, so looks like anything x less than 0. X strictly less than 0, I'm getting outputs. I'm not getting any outputs between 0 and up to 2. But if I'm plugging in values bigger than 2, x bigger than or equal to 2, I will get outputs. So this is the domain of the function. Notice I kind of glued these two pieces here together. So this would be like x from -infinity all the way up to -3, and then from -3 all the way up to 0. So that's why really just x less than 0. And then x bigger than or equal to 2. If you want to write this in a different notation, you could have written this as going from -infinity all the way to 0, and then from 2 all the way to infinity. And I'm going to be including the 2, so I'll put a square bracket here. Okay, let's talk about the range. The range of f. So just as a note, you could write all f of x, since I'm talking about all my outputs. If you don't like using f of x, y is equal to f of x. So usually when books or teachers write y and f of x mean the same thing. It's whether I'm just using function notation or not. So if you don't like writing f of x here, if you want, you could write y. So all y's, or all outputs such that, well, what could y be? Well, if I'm plugging in any number between -infinity all up to a -3, the output is always -2. So a possible output is y equal to -2. Okay, so I'm going to get an output of -2. I don't get outputs anything between -2 and looks like all the way up to 2. But I will get an output of 2 and anything bigger. I will get an output of 2 and anything bigger. So I could write all y could be equal to -2 or anything bigger than or equal to 2. Okay, so this will be the range. If you want to write this in interval notation, if I'm just including a point -2, what I'll do is I'll put square brackets on -2. I'll write and. Also, I could go from +2 all the way to infinity. So either way would work. Here's the domain and range. Okay. So let's go ahead and do some evaluations. Okay, so let's evaluate. I want you all to evaluate. How about f of -4, f of 3, f of -2, f of -3, f of 0, and f of 1. So go ahead and pause the video and try to evaluate this piecewise function at these points here. Okay, let's do it together. All right, so oftentimes when I'm evaluating piecewise functions, I don't really look at the graph. I usually just look at the piecewise formula. Okay, so I want to plug in a value that's -4. So where am I? Well, -4 is less than -3. So when I plug in -4, the output is always -2. So there's the answer for this one. If I'm plugging in the value of 3, let's see, 3 is bigger than 2, so I'll use this version of the function. So when I plug in 3, I get an output of 3. So there's this one. Okay, let's go ahead and plug in -2. So let's plug in -2. Let's see, where is -2? Well, -2 is not less than or equal to -3, but -2 is between -3 and 0, so I'm going to plug -2 into this function. So that'll be a 4 minus a -2, so that'll be 4 plus 2. I'm going to get an output of 6. Okay. Let's say I evaluate this function at -3. Now this is where it can get a little bit confusing. You have to look where the equal sign is. So when I'm plugging in at -3, there's a -3 here, and there's a -3, but this less than or equal sign mean that if at -3 I'm using this function, and this function here is not defined at -3. So we want to look for where the kind of bottom slashes or the less than or equal sign is. So when I plug in -3, the output is -2. Okay. Let's go ahead and evaluate this function here at 0. Okay. Well, notice here that my function is not defined at 0. Notice that this is a strictly less than symbol, so the function is not defined at 0. Okay, so I would need to go to the next spot to see if even 0, the function is defined at 0, but the next spot says that x is bigger than or equal to 2, so notice that this function is not defined at 0. It doesn't tell me anywhere what it means to plug in 0. The function's undefined at 0. I'll just put und for undefined. Okay, similarly, if I try to plug in 1, 1 is not between 0, 1 is between 0 and 2. There's nowhere in this list that tells me what to do when I plug in 1. So, similar to the last one, f of 1 is not defined. Or we'll write undefined. Okay. Beautiful. Let's do another example. What I would like to do here is I would like to talk about some piecewise functions that we actually already know, but maybe don't realize that they're piecewise. So there's a toolkit function that is defined piecewise, or that we can see it defined piecewise. Okay. What I'd like to say here is we already know a piecewise function. Or at least if you took Math 99, you should be familiar with this function. It's one of our toolkits. It's the absolute value function. So the function f of x, which is equal to the absolute value of x, this function is defined piecewise. So remember what the absolute value function looks like. It's the timeless, the classic. It looks like a V. Well, why does it look like a V? Well, notice what the absolute value does. What the absolute value function does is when you plug in a positive value, it keeps it positive, If you plug in a negative value, it takes that negative value and makes it positive. So when you plug in 0, the absolute value of 0, well, that'll just stay 0. The absolute value of 1, that number is positive, so it stays 1. If you plug in 2, 2 is positive, so the output is 2. So on the right-hand side, it looks like the graph y equals x. But now if I plug in -1, it takes the negative number and makes it positive, so the absolute value of -1 is 1. The absolute value of -2, it takes -2 and makes it positive, it'll be 2. This is the graph of the absolute value function. So this is f of x, which is equal to the absolute value function. The timeless, the classic, the v. Okay, notice that if I wanted to, I could define this function piecewise. And I'm going to define it just in kind of the normal way how we kind of talk about the absolute value function. What does the absolute value function do? Well, it says, well, what would you do? Whatever value you plugged in, you wouldn't do anything to it. It would stay the same. For example, if you plug in 2, you get out 2. If you plug in 10, you get out 10. If you plug in 100, you get out 100. When does the absolute value not change the number you plug in? Well, that's when it's positive. So that's when x is greater than or equal to 0. Now, when does it change? It flips the sign of the number when it's negative. So what happens when x is negative? Well, if it's a negative number, like if you plug in negative 2, what does it do? It makes it a positive 2. If you plugged in negative 3, what would it do? It'd make it a positive 3. So if you plug in a negative number, you got to flip its sign. How do we flip a sign? Well, recall that 2 negatives make a positive. So if I take that negative number and I slap it with another negative, it'll make it positive. Notice how this is going to work. If I evaluate my function, let's say at 3, for example. Well, 3 is bigger than 0. What's it tell me to do? It tells me to keep the number the same. Similarly, what if I plugged in negative 4? Well, negative 4 is less than 0, so I use this version of the function. So I'll replace the x with a negative 4. A double negative makes a positive. Beautiful. So that's how the absolute value function here works. Okay. What I would like to do is I would like to do another example of just graphing absolute value functions and thinking about them piecewise, or writing an absolute value function in terms of a piecewise definition. Let's do another one. Okay. So let's go ahead and this will be an example. Let's go ahead and write f of x, which is equal to the absolute value of 2x minus 4 as a piecewise function. So go ahead, pause the video, and see if you can do this one here on your own. Okay, here we go. So I have to recall how the absolute value function works. Notice that if whatever is on the inside of the absolute value bars, if it's positive, it stays the same. If whatever's inside of the absolute value bars is negative, it's got to flip its sign. So let's go ahead and start with that. So let's go ahead and write f of x. That'll be equal to, well, when am I not going to have to do anything to the inside? When can I just keep it as 2x minus 4 and not worry about flipping a sign? Well, in this case, what I want to know is well, for what values of x is 2x minus 4 positive? If this value is bigger than 0, I don't have to change it. So I need to solve this inequality. Recall when you solve an inequality, it's just like solving an equality, as if there was an equal sign there. You just have to remember, if you ever multiply or divide by a negative number, you got to flip the sign. So how about we add 4 to both sides? And then we can divide both sides by 2, so x will be bigger than 2. Since I'm dividing by 2, it's a positive number, I don't have to change the sign. So if I plug in any value into this absolute value here, any value to this function that's bigger than 2, the inside will be positive and I won't have to do anything. So it's going to be 2x minus 4, provided that x is bigger than or equal to 2. Okay, and you could just kind of test this. For example, if we plug in 2 exactly, I would get 2 times 2. That would be 4 minus 4. I'd get out 0. Okay, the absolute value of 0 is 0. Okay, but if I plugged in like, 3, for example, f of 3, that's going to be the absolute value of 2 times 3 minus 4. Okay, since I'm plugging in 3, that would be what? That would be 6 minus 4. That'd be the absolute value of 2, which would just be 2. I didn't have to change what's going on the inside of the absolute value bar because what I plugged in gives me out a positive value. Okay, but what happens if I plug in something that's less than 2? Less than 2. Well, if you plug in something less than 2, what's going to go on inside here is what's going on inside will actually be negative. It'll be negative, and I got to flip the sign. So I'll show you how this works. So I'm going to take the 2x minus 4. If I plug in a value less than 2, like for example, let's say if you plugged in 1. If you plug in 1, you get 2 times 1, which is 2. 2 minus 4 is a negative. So it'd spit out a negative 2, but I need to make that negative 2 a positive 2, so slap it with a negative. So here, I've defined this absolute value function, the absolute value of 2x minus 4 piecewise. And again, just to kind of show you how it's working, if I were to plug in, like, I don't know, something less than 2, let's say I plug in, I don't know, how about I plug in 0, for example? Well, if I plug in 0, okay, I would use this version of the function. That'd be a negative 2 times 0 minus 4. So I get out a negative. I get 0 minus 4. I would get out a negative 4. A negative and negative makes that a positive 4. So it's. I know if I plug in something less than 2, 2x minus 4 will be negative. I'm slapping it with a negative to make it positive. So that's how we can define this function here, piecewise. Beautiful. Okay. Let's do one more example. I want you to do the same exercise. I want you to write. Go ahead and write. Let's call this function h of x, which is equal to, how about 3x minus 5 as a piecewise function. Okay, go ahead and give this a shot. Okay, let's do it. So if I want to write this function as a piecewise, this absolute value as a piecewise function, okay, what I want to do is I write, let's see, h of x, if I want to write it as a piecewise function, okay, well, I have to think about what happens. What I want to think about here is when the inside of the absolute value bar is positive, I don't have to do anything to it. So I want to keep a 3x minus 5, provided, well, for what interval is this going to happen? I have to think about when is 3x minus 5 positive. It's bigger than or equal to 0. Okay, well, I could add 5 to both sides, so I get 3x would be greater than or equal to 5. I could divide both sides by 3, so when x is bigger than or equal to 5/3. So if x is bigger than or equal to 5/3, if I plug in a number bigger than 5/3 into 3x minus 5, it's going to spit out a positive number. So when I do the absolute value of a positive number, it doesn't do anything to it. Okay. Well, now it's going to flip sign. If I plug in something that's less than 5/3, this will spit out a negative number, and I need to make that negative number positive by slapping it with another negative. And there we go. Here is the piecewise definition, the piecewise definition of this absolute value function. Okay. I hope you enjoyed this lecture. We'll see you in the next one. Take care.